modeling of PV cell, PV module, PVFA we have seen. Okay. Then last class we have also discussed about mathematical modeling of PV array configurations we have seen. So we have a series, parallel, bridge link, honeycomb configurations are there. Okay. So today we are going to see so what is a grid connected PV systems and about standalone systems we will see. So these are the things yesterday we have discussed already. Even few numericals we have solved. Okay. I hope this much is we have completed. See, till here we have seen yesterday, isn't it? We have a configurations of series parallel is there. Sorry. Okay, let me show you first onwards. See. So if you have a series configuration, I explained yesterday. So if it is a 49 PV modules are there. So what will happen? So currents are same in the series configuration. The current of the PV will be equal to current of the module. Okay. So current flowing through all the modules will be same. Whereas the voltages will be, the voltage across the VPV will be equal to summation of all the voltages. Okay. In the series configuration, the currents flowing through the PV system will be equal to the single module current, since current in the all the modules is same. When it comes to voltages, the voltage across the VPV is, then it will be summation of voltages of all the modules. Power will be the multiplication of VPV into IPV. This is 49 Vm into Im. Similarly, parallel configuration, which is used for low voltage and high current applications. So here it is reverse. The voltage across the VP will be equal to voltage of one module, because parallel circuit, all the modules are connected in parallel. So 49 modules are connected in parallel. The voltage of VP will be equal to voltage of one module, and currents will be in the parallel circuit. The currents will be added together. So it is 49 into Im. So similarly, series parallel configuration we have seen yesterday. In that, there is 7 by 7 structure we have taken. In the series parallel structure, in a string, the modules are connected in series and the strings are connected in parallel. In a string, the modules are connected in series, whereas the strings are connected in parallel. Okay, each string is connected in parallel with other string. In parallel with other strings. So this is what series parallel configuration. So here how the voltages will be, voltage across the VP will be equal to voltage across one string, which is nothing but 7 times the module value. The current flowing through the string will be equal to current flowing through the module. So current flowing through the entire PV is IPV will be equal to the current of string 1, string 2 and so on, string 7. So it will be 7 times, it is also 7 times the string value or 7 times the module value. So it is also you will get, so it is for medium voltage, medium current applications. Similarly, bridge link is a combination of, so here what we have considered, so 4 bridges together it will be considered. So one tie will be taken, next 4. So bridge link also similarly it will be like medium voltage, medium power applications. Honeycomb structure is taken with honeycomb, that is 6 ties. Then after that one more. So that combination honeycomb structure will be taken. So here also the medium voltage, medium power application. Yesterday already we discussed these things. Then total cross tie. Next is total cross tie. Total cross tie means all the modules are connected together. When all the modules are connected together, so what happened? So the voltage across VPV or voltage across the entire PV string will be equal to the voltage across first row 1. This is entire row. Voltage across second row, voltage across third row. So it is VPV will be equal to V rho 1, V rho 2, V rho 3 and so on, V rho 7. The currents will be the module currents of the first one, 8, 15, 22, 29, then 36 and 43. So here also 7 times the VM we will get, 7 times the IM we will get. So this is also used for medium voltage, medium current applications. I told you already. So even uh, among all the PV configurations, so among all the configuration, TCT will give you the best one. So now when we consider this one, this is the conventional configurations. Now people are going for hybrid configurations also. What is meant by hybrid configuration? So when you go ahead with, suppose instead of here, what we are doing, 6 by 6 is conventional, series parallel, TCT, bridge link, honeycomb I have taken. Now what I am doing, in the hybrid configurations, top these panels are, this is series parallel, this entire thing is cross tied, and down one also series parallel, series parallel, series parallel, cross tied. So this is, top one is bridge link, down one is bridge link, bridge link, cross tied can be taken. Even there is a possibility, okay, honeycomb, even top one is series parallel with the TCT can be taken, and bridge link with the TCT also can be taken. There are so much research is going on hybrid configurations also people are working. Okay, so we'll try to see. Already these numericals yesterday we have solved. Okay, so I will come back to this numerical later, but first let me explain you. So today I will explain you about standalone and grid connected systems, what components we are using in the PV system. Then after that I will try to give you about what is standalone system, what is grid connected PV system. I will try to explain it. Okay, so when you consider a PV system, so there are three things are there. Okay, one is power supply and energy storage, that is the one component. The second component is interfacing circuit. Third is loads. Okay, so when you consider, so here, so in the PV system, what we have is, the power is supply and energy storage element. Here we are having different type of supplies can be there. Okay, it is rooftop PV with grid can be connected, rooftop PV only solar, with the help of solar farms energy can be generated, rooftop PV wise energy can be generated, even PV integrated EV charging stations also can be taken. Try to understand, in the solar PV system. Okay, if I want to integrate PV system with a grid, so here we are having, what we are having is, the power can be generated in the form of solar parks. This is one. Second one is, the solar power can be generated in the form of rooftop PV systems. Third one is, a PV integrated EV charging stations also can be taken. Here if you observe, this is PV panels and PV integrated EV charging stations we have taken, and along with that we will consider batteries also. Okay, and even sometimes online grid connection also will be there. Now what happened, you consider a solar PV farms which is generating high amount of energy. If it is online grid connected, no issue. Okay, then if you consider rooftop PV systems, but rooftop PV systems you can't say like always it is connected with the grid. So sometimes off grid also will be there. So in that case, if loading is not there, excess power is available, so that can be stored in the batteries. Sometimes during morning times or afternoon times, when there is an excess power is there, rather than the loading condition, which can be stored in the battery, and during night time whenever required, whenever the sun is not there, so that time from the battery can be taken. You understand, we are having different types of supplies are there. Okay, so based on it is household purpose we can consider, or that means residential purpose we can consider, industrial purpose, commercial, or maybe grid integrated also can be taken, utility. So solar PV farms mainly it is considered for utility purpose. Try to understand. Solar farms are mainly considered for utility purpose. Rooftop PV systems are mainly considered for household, residential, commercial purposes. And EV PV charging integration systems are mainly considered for EV charging. If excess power is there, then it is connected with the utility. Or else the power will be stored in the battery. Fine. Solar PV farms are used for utility purpose, rooftops, residential commercial purpose, and EV PV charging stations for charging the EVs, and excess power is there that can be stored in the battery and can be reused, or else it can be connected to the grid also. Now, what we have the interfacing elements? We have different interfacing elements are there. We have a charge controller, distribution box, power flow controller, energy meter, DC-DC converter, and inverter circuits. Okay, so what is the charge controller? Okay, what is the purpose of charge controller is, the first one is the charge controllers will regulate the movement of DC power from PV panels to either. Okay, so it will regulate the power from the PV panel, either it can be from solar PV system, or it can be rooftop PV system, or it can be PV integrated EV charging station. Okay, it is used as so regulating power from here to other side. Okay, here charge controllers, mainly two types of charge controllers we will use. So here I have written it. Okay, so it prevents the overcharging of the batteries. So mainly two types of charge controls are there. One is maximum power point tracking we will use. Second one is pulse width modulation. Okay, so why we will use these things when it is required? During uniform conditions, MPPT not required, but during shading conditions only, to extract the maximum power, these things are required. Okay, so when it comes to PWM is traditional use for small solar systems, whereas MPPT is suitable for larger systems. I hope you understand. So in this charge controller, why we are using is to regulate the DC power supply from PV panels to the battery bank we are considering. Okay, it prevents the overcharging of the batteries. Okay, how much is required, it is automatically cut off will happen. So two types of controls we are using, one is MPPT, one is PWM. For small scale, PWM is sufficient. If it is a large scale systems are there, we are using MPPT. Hope it is fine. Second one, same like charge controller, we have a power flow controller also there. What is power flow controller is a more advanced version of a charge controller. Okay, so it is used for multiple power sources which have to be interfaced with loads and the battery bank. Power flow controller is, you might have studied unified power flow controllers, UPFC, unified power quality conditioners, UPQC. What is the purpose of that? When you use power quality or power flow controllers, UPFC, UPQCs, so it is a hybrid controller. When there is a power quality issues are there, if there is a deviation in the voltage, or if there is a deviation in the current, or there is a deviation in the frequency, what will happen? So we need to inject the voltages, we need to inject the currents, or we need to look after both. Sometimes voltage will be injected, sometimes currents will be injected, sometimes both need to be injected to maintain the power flow limit properly. So in the power flow controller, what we are doing here, charge controller is just simply, it is able to control how much amount of charges required, then automatically turn off, turn on, it is regulating device. Okay, but charge controller with MPPT, if you consider, then extraction of maximum power is possible. Rather than that, in bigger plants or in extra high voltages, UPFCs will be used. Power flow controllers can be used, okay, to maintain the system harmonic free. To maintain the system harmonic free, okay. So power flow controller also can be used. Then battery banks. Okay, so everyone knows when there is an excess power is there, battery banks will be stores the energy from the PV panels. When deficient power is there, battery banks will give the energy. So what does it mean? So the battery bank enables you to optimize your utilization of solar energy and serves as a dependable contingency plan during when there is instances of power grid failures. Okay. Okay. So energy stored in the PV array is stored for later use instead of immediately consumed. So, so here you can observe one more thing. So we have one more thing is that here we are controlling, we are generating the DC power. Charge controller is regulating the DC power supply, but here your DC-DC converter is there. What is the DC-DC converter? If I want to boost the voltage to higher level, if I want to boost the voltage higher level, so here I can use different type of DC-DC converters can be used. It can be unidirectional or bidirectional. Generally bidirectional converters will be used. So converter can be used, so we will step up the voltage levels, then inverter will be used to step down the voltages. Try to understand. The power flow controller is for extra high voltages, that is after the inverter it will be connected. Charge controller is, see, we have a supply. One is through solar farms we are generating, second one through rooftop we can generate, third one is PV integrated EV charging stations can be generated. So one is utility related, very large amount of powers we are generating. Second one is rooftop PV system, small amount of power we are generating which is sufficient for household purpose. Third one is EV-PV charging station we are generating. How much is sufficient for EV-PV charging integration, or EV charging, how much is required. So if excess power is there, it can be given to the grid or the batteries will be stored. So when it comes to the charge controller will regulate input how much you are giving the power supply. It tries to give to the DC-DC converter. It will be connected to DC-DC converter. Suppose your load is DC load, then directly it will be connected to the DC load. As per your DC load condition, DC loads will be connected to the converter. If your loads are AC, then it will be converted the inverters. This one. Is it okay? And now we have two things are there: energy meter and distribution board. So with the help of the energy meters, then what we will do, we will measure the how much amount of power is transmitted, how much amount is consumed, or what is the power flow rates will be measured in the energy meter. So distribution box is enables you the relay operation. So either on and off or whatever is required. So maintenance purpose, if you want on and off switches, then will be taken care by distribution board. I hope you understand. Power flow is mainly for extra high voltages after the inverter will be connected. So okay, these are the parts we have. So one is supply related, second one is interfacing elements, third one is loads. Now the first we will try to see. Next one, we have different types of PV systems are there. First one is standalone PV system. Second one is grid connected PV system. It is classified into mainly standalone PV systems, grid connected, and there is a hybrid systems also can be considered. Hybrid is nothing but grid connected only. Okay. So the scope of solar PV systems, as you are aware, significantly increased in recent years. Okay. So why? Because of its additional growth. Okay. So and due to its modular structure. Okay. So when you consider a standalone PV systems, it is also called as off-grid PV systems. Standalone PV systems are also called as off-grid PV systems. Okay. So these things will rely on only solar power. Okay. So what will happen? Whatever the, you try to understand difference between standalone and grid connected is, in the standalone PV system, you will install the PV panels on the rooftop of your house, and which will be consumed by your house itself. If it is a residential standalone means you are not connecting your system to the load, sorry, you are not connecting your system to the grid. Without connecting your system to the grid, that means it does not mean you are not taking the power supply. Even in standalone PV systems, even islanded condition you take. Somewhere some person is there where there is no power supply. There also you can give the power supply to the people wherever the sun reaches there. Even though power supply not there, separately you can, how much amount of load is required, that many PV panels can be kept, then you can extract the maximum power. That is meant by standalone system. Without connecting to the grid also, if you have a AC loads or if you have a DC loads, you can extract the power from the sun. I hope you understand. So here what happened, you have installed a rooftop PV system. You have installed a rooftop PV system, and let us consider you are in the island condition. Island means you are, don't have connectivity with any of the grid connection. You are relying on only, you are relying only on rooftop PV system. Then what happened? So sun, from the sun you are extracting the power during morning session only. Night time there is no sun. So then what is the, then night time, then you will have a, you will have to face a problem that, so without power you need to stay. So to avoid that, in standalone systems it is mandatory to have a batteries. Compared to grid connected PV systems, in standalone systems the people will suggest it is mandatory to have a battery. Why? So when there is a morning excess amount of power is there, the battery gets charged during the morning times, and some amount of power will be utilized. Some amount of power we are utilizing for household purposes. Some amount of power will be utilized for charging your batteries. After that, what we will do? So here charge controller will regulate how much amount of power is available here, how much need to be dumped here. So everything will be controlled by charge controller. Here what we will do, suppose at your home you might have two different loads are there. Few AC loads are there, few DC loads are there. 90% is AC loads only. So if you have a AC loads, both the DC loads are there. So what we will do, if extremely it is only DC load, then you will use DC-DC converter. The based on how much amount of power is required, that much amount of power will be given directly. But if it's AC load is there, so what we will do? First we will enhance the power of DC power. What does it mean? With the help of DC-DC converter, what we are doing? We are increasing the voltage limits, and then we are using DC to AC inverter connection. Then we are connecting to the load. What is the significance of converter inverter here? If I use small DC converter, what will happen? If I consider a little bit of bigger one, what will happen? We should understand. So try to understand. It is PV panels are taking so much of place, and PV panels are giving only 20% of efficiency to you. Okay, so PV panels are giving 20% of efficiency, and PV panels are occupy more amount of space also. Now, if I want more power and I have a limited space is available, then what I will do, I will try to consider the best bidirectional DC-DC converter in such a way that, so high gain converters will be considered, and you will enhance first, or you will convert with the help of high gain converters. Okay, so what we will do, we will boost the voltage. Then after that, after boosting the voltage, then we will go for inverter structure, then connection will be done. So with the help of converters, if you consider, then what will happen? Burden on the PV panels will be reduced. Suppose you assume that this converter not there. What will happen? How much amount of DC load power is required? That much it has to generate. Or how much AC loads are there? That approximately that much I need to generate, and which will be converted to AC and which will be connected. If DC-DC converter is not there, then what will happen? The entire amount of energy, how much required by the DC load, it has to convert directly. And how much amount is required for AC loads, then the DC power generated will be given to the inverter, and which will be connected to AC loads. Here what will happen? Burden on the PV panels will increase, size of the PV panels will increase to meet the criteria. Okay, so with the small amount of space, with good converter, then what we can do, we can easily supply power to the DC load and AC loads. I hope you understand. Next, grid connected PV systems. So when it comes to the grid connected PV systems, what we'll have is in the difference between standalone and grid connected is standalone systems we are generating the power, and what we are doing, we are consuming the power ourselves only. The prosumer and consumer, we only. We are producing the power and we are consuming ourselves without connecting to the grid. But here it is not like that. When a grid connected PV system, what we will do is we will generate the power with the help of big solar parks. If we generate a power with the help of big solar parks, that power should be controlled by not the charge controller, by the power flow controller, it will be controlled. Okay, after that, which will be given to DC-DC converter, which will be given to inverter, which will be connected to the grid. So this is, there are so many solar parks are available in India. Okay, even largest solar park in the world is, it is in India only. Okay, so here what we are doing, with the help of solar parks, we are generating the power, and which will be enhanced with the converters, and which will be inversed, and which will be connected to the grid. This is one way. Or else, even if you take commercial buildings, here three applications are there. One is utility level. In the utility level, one is utility level. In the utility level, solar parks are connected and directly giving to the grid. Second one is this one, you see, rooftop on the commercial buildings. Second one, rooftop on the commercial buildings. If I consider rooftop on the commercial buildings, what is happening? If you observe here, on all the rooftop panels, there is PV panels are there. So here, if I consider this one, what is required? I want little bit of medium converter is required. Then which will be inversed. Even some amount of power which is generated will be utilized by that buildings itself. Suppose in the solar parks, whatever the power is generated, which will be connected to DC-DC converter, which will be dumped to the grid. This is only for the utility purpose. Whereas rooftops of PV panels on the commercial buildings, whenever if we install, first what we will do, we will try to consume, or we are producing, and we will also consuming some amount of energy, then remaining surplus power will be connected to the grid. Similarly, even your at household also, see, if you have a more amount of PV panels are there, so how much you need for home, rather than that, I have a excess amount of power is available. See, I want 50 kilowatt, but I have a 100 kilowatt power I am generating. What I will do, remaining 50 kilowatt power can be given to the grid. Right, understand? In the standalone PV systems, what we have done, so we try to do, we are trying to generate the power. What we are doing, we are utilizing entirely for household purpose, or else some amount is stored in the batteries, utilize it in the night. Whereas grid connected PV systems, so excess power anything is there, which will be connected to the grid, or which will be injected into the grid through converters and inverters. Understand? In the utility grid, solar parks, straight away it will be connected to the grid. In the commercial buildings, some amount will be utilized, and remaining amount will be given to the grid. Or even in the rooftop solar on small houses also, small amount of power will be utilized for the purpose of loading conditions. Remaining power will be dumped to the electric grid. Is it okay? So here one thing. So when you are designing a converter for rooftop houses, small houses, then converter required is small in size. Why? When you design a converter, you have to know output voltage, output current, output power, as well as ripple in the current, ripple in the voltage. If you know, then only converter could be designed. Isn't it or not? If I want to design a boost converter, I should know the output current, output voltage, output power, ripple in the current, ripple in the voltage. Okay, if everything if I know, then I can design a converter. So here what happened? So for rooftop on small houses, we need size of the converter will be smaller. So rooftop solar on the large commercial buildings, the size will be little increases, but it is a medium level of converter can be used. Why? Some amount you are utilizing for buildings only. But whereas in the solar parks which we are considering, the solar parks what we have, the solar parks huge amount of power is generated. There is no consumption at all there. So entire thing 100% will be dumped to the grid only. Okay. Now, hybrid systems. What is hybrid systems? A similar more or less you are grid connected only. Here extra is what we have is along with the solar parks in residential complexes, even diesel generators can be used. Okay, along with solar parks, rooftop systems on houses, rooftop system on buildings. Along with that, even we can consider diesel generator also. Okay, so if you say hybrid PV system, here we are considering integration of solar parks, integration of building rooftop PV systems, and integration of DCs. Then we will connect to the grid. That is one way. Or else, if I say hybrid power system, if I say, then even wind, even other things also can be included. So here also as like that, when solar parks are there, it will be directly connected to the utility grid. When commercial buildings are there, some amount will be consumed and remaining will be dumped to the grid. Rooftop also similar. So here only extra thing is whenever deficiency power is there, with the diesel generator we can take that. That is possibility. Now we are telling like solar parks are big sizes there. So we have different architectures are there. What is that? We have a central architecture. We have madam, I'm in class. I'll call you at 5. Okay. Okay. We have central PV architecture. We have a string architecture. We have a multi-string architecture. Fine. We have a 3 different. See, try to understand. We have these are the PV components we have. What is that? Power supply, interfacing, and different loads are there. Now after that, what we have seen, we have discussed about standalone PV systems. Standalone means only utilized for that particular house or that particular building. Grid connected system means so we are generating the excess amount of power which is connected to the online grid. Okay, it is called, that's why it is called on grid. Previous one was off grid. Okay, hybrid also on grid system only. Now these systems, there is architecture can be, we have a different architectures are there. One is central PV system architecture, string PV architecture, and multi-string PV architecture. What is the difference between name itself? Central PV system architecture. What is meant by central PV system architecture? So we have n number of like this solar parks are there. Let us suppose solar parks are these many solar park panels are there. All the panels together, central architecture, no, entire PV system all together will be connected to one converter, will be connected to inverter. Here MPPT technique we are using and which will be connected to loads. So central PV system architecture is nothing but entire your solar park, or if you consider solar park, entire solar park will have only one DC-DC converter. Only one inverter we are taking and MPPT, and it is connected to load. So which is not feasible for solar park system. But central PV system is feasible for low ratings. That means for a rooftop uh, buildings or rooftop houses. Okay, for rooftop PV system of houses, central PV system is can be considered. Why? The size of that rooftop PV house system is very small. You understand? Size of the rooftop PV system is small. So for the small amount of size of the PV system, the converter can be smaller and inverter can be smaller, so easily you can consider loads and easily consider grids. Now if it is going to buildings, now from one small house to, now you consider there is maybe apartment to take, normal apartment with 5-story building is there, no problem. So we can consider one DC-DC converter, no problem. You have a multiplex building is there, like one shopping complex is there of 5-story of shopping complex, then what will happen? The huge amount of panels will be there on that. So here some normal 5 kilowatt to 50 kilowatt something, no issues. But more than that, if you are generating, central architecture is not suitable for high ratings. So what we need to go for? Second one, we need to go for string architecture. String level architecture will be used. How it is? Now a one string of PV panels will be connected to one DC-DC converter. So for all these PV panels, it is connected to one DC-DC converter, MPPT, then inverter, then aggregation will be connected to load. Second string will be connected to another converter, then load. Similarly, in the string integrated PV system architecture, each string is provided with one converter. I hope you understand. The previously, the entire PV system is provided with one converter and one inverter structure. Okay. Now, in the string integrated converters, so which is modified, and what is that? Each string, what we are doing, each string we are providing a dedicated converter, a dedicated inverter will be given. I hope you understand. Okay. So here what happened? So with this setup, okay, so the power rating, even though it increases, suppose buildings you take 1 megawatt or 2 megawatt power is there, or up to 10 megawatt power is there. So one string with maybe 50 kilowatt, one string with 5, like so. Every string with small converters can be kept. All the converters can be aggregated together. Loads will be catered, or separately can be catered, or entire power can be combined, and then you can connect to the load, or separately you can segregate and you can connect also. That's what string integrated converters. What you are doing is, rather than considering one converter, we are considering multiple converters string wise. Here there is an advantage is there. What is the advantage? First we will see the disadvantage of central converter. In the central converter, if a DC-DC converter has a problem, or if an inverter have a problem, what will happen? PV you are generating, full amount of power you are generating, but any one of the component having a problem here in the either DC-DC converter or inverter, what will happen? The entire loads you can't provide any supply. But the string integrated converters, even though fault on, suppose there is a fault on this converter, but but other strings are connected with remaining all converters, no, which could able to give the continuity of power to the loads. All are aggregated. These all the things will try to cater the loads. So that is also one more advantage. Okay, but here again this power will be string integrated converters also will have a limit. Why? It can't be used for solar parks. It can be used for commercial buildings, okay, up to some medium level ratings. But if a big solar park is there which is generating 1000 megawatt power, the in India, what is the biggest solar park is in Badla, it is there. So what is the rating, So there is one plant is generating how much, 2000 megawatts of power is it is generating. Okay, so highest power plant is solar power plant is available in India only. So one power plant is generating 2000 megawatt. 2000 megawatt one converter if I keep, will it work? Definitely not. So central converter is not suitable for solar parks. So 1000 megawatt also solar parks are there. 2000 megawatt solar parks are there. 500 megawatt solar parks are there. When you have a solar parks with 500 megawatt, all panels together, one converter if I consider, it will damage. So even string also can't be considered because of high power ratings. Even string converters also not suitable. So what we will do is we will go for multi-string. Multi-string means instead of, see, previously what we have done, all panels together it is connected to only one converter, that is central. Now in the string integrated converters, entire one particular row, all the entire one particular row or entire one particular column will be provided with one converter. Now in that row, some amount of modules will be connected with one converter, other modules will be connected with other converters. Then so group wise we will consider in the multi-string converters based on the ratings, some group of converters together will be connected to one converter, other group of converters in that line itself to the another converter and inverter topology, and so on. Then there is another group is connected to like this. So here in the multi-string, the main thing is, so instead of just the entire string with one converter, so in that string itself there are limited to particular number of strings will be limited to based on the capacity of the DC-DC converter, capacity of the inverter structure. Then what we will do, we will make the groups, how many number of panels to be included in the first string, how many number of panels to be taken in the second string. So like that multi-strings will be considered. So mostly preferably all the systems will have, mostly in the solar parks, in the utility level, people will consider multi-string system. In the building integrated circuits, string integrated converters will be used. This is called string integrated converters. This is called central converter. Okay, there is one more thing is there, distributed MPPT. Nowadays people are also working on distributed MPPT. What does it mean? Each panel will be provided or each module will be provided with one converter. That is too costly. That is too costly, and which is very costliest solar power plant it will become. So we have a central converter structure is there, we have string integrated structure is there, we have multi-string structure is there, even distributed MPPT also people are working. But the problem is in the distributed MPPT, each module or each PV panel or each module will be provided with one converter, then which leads for smaller amount it is okay, but if it is a large amount of plants are there, complexity of the system will increase, number of modules will increase, the cost of each equipment will increase, then there will be a problem. So the preferred thing is for utility purpose if multi-string, for commercial buildings string, for household purpose central. You can't use vice versa. At your home you no need of multi-string or string because the power ratings are small. Is it fine? So before going to the list of solar parks, just I would like to show you yesterday 2 3 numericals are there. We will solve and we will go to that applications. That will be better. So there is a different type of solar parks are available in India. Size wise, I will explain you. Okay. Yesterday also I could not get time to solve some numericals. So first we will solve that numericals. Then I will go to solar parks. We have a different solar parks located in India. So size wise, I will explain you. Okay. So then after that, some solar applications are there. Then MPPT techniques are there. Okay. So first, let me go. I hope you understand. We have we have discussed about various components available. Various components available we have discussed. Then after the components, we have discussed about standalone PV systems. Then we have seen grid connected PV system, hybrid PV systems, central PV architecture, string PV architecture, multi-string architecture. So let us solve that 2 3 numericals. Then I will go to that list of solar parks I will go. Otherwise, I hope this one we have designed. This one can you take? Design a 7.2 kilowatt PV array which can generate a maximum voltage of 158 volts and a maximum current of 46 amperes. Design a 7.2 kilowatt PV array which can generate a maximum voltage of 158 volts and a maximum current of 46 amperes at standard test condition. Also mention what kind of configuration is it and draw the same. And try to see we need to design a 7.2 kilowatt system and with a maximum voltage is MP is 158, IMP is 46. Okay, but here he has given the maximum power of one module is 200 watt. Maximum power of VMP, voltage at maximum power point is 26.3. Current at maximum power point is 7.61. Now if you observe, voltage of one module is 26.3. Your total voltage required is 158. So compulsory number of modules to be connected in series should be more than one. Now current at the maximum power is 7.61. So current of your system is 46 amperes. So it should not be series or it should not be parallel. It can be series parallel. Now how many number of elements are in series? How many number of modules are in parallel? Can you say? Given data is PV array has to generate maximum current of 46 amperes. PV array has to generate maximum voltage of 158 volts. So this is the single PV specification is given to you. So how to solve? Yesterday we have solved. Now single PV module can generate 200 watts. So then how many number of
6 by 6, sir.
Okay, sir. 6 are in
6 are in
series.
parallel and 6 are in series.
Yes, good, sir. Correct.
Yeah.
So now, total number of modules required are how many, sir?
36.
36. So number of PV modules required is 36. It is 7.2 kilowatt by 200. It is 36 modules. Okay. Number of modules to be connected in series is total voltage. Total voltage is 158 by voltage of the single PV module. Voltage of the single module is 26.3. So 6 should be in series. Next, number of strings to be connected in parallel is total current required is 46.
46.
Single module current is
7.6.
So you need 6 cross 6 structure. Is it okay? No. Next one. Can you do this? A solar cell has an output capability of 0.5 amperes. A solar cell has output capability of 0.5 amperes at 0.44 volt. A series parallel solar array has been designed of such cells with 100 parallel strings. Each string has 300 cells in series. We have 100 parallel strings are there. Each string has 300 cells in series. Then what is voltage capability, current capability, and power capability? It is so easy. Total amount of voltage will be what? Suppose if you consider in a string, how many cells are there? 300 cells are there. Voltage across all 300 cells will be how much? Do you understand? The question is, this is 100 parallel strings are there and each string 300 cells in series. Okay, so in a string 300 cells are there. So voltage across the PV system will be equal to voltage across one string. Voltage across one string will be equal to 300 cells. So 300 cells into
0.44.
Yeah. Yes, sir. How much
132.
voltage capability of single cell into number of
Cells
series
connected in
connected
series.
cells? Okay. So how
That
much
is
it is? One.
132 volt.
Yes, sir. Yes, sir. Next, current capability will be how much? Current capability is current flowing through the 100 strings. Current
50
capability is
ampere, sir.
yes, sir. Current flow. 50, sorry, this is amperes. Sorry, by
Yes.
mistake. By mistake, I have written code. Typo error. Okay. Next, what about power capability? Already
Voltage
was
into
seen.
current.
So it is 6.6 kilowatt.
Kilowatt, yes.
No. Can you see this? Solar insulation of rectangular module we have taken. Size is 1.5 meter by 2 meter size. A photovoltaic cell is 750. Solar insulation is 750 watt per meter square and area is 1.5 meter by 2 meters. If the efficiency is 15%, what will be the power output? Efficiency is equal to power output by power input. Last class we solved. Efficiency equal to output power by input power. So output power by input power is how much? Insulation into area. Hello. Yes. Yeah, tell me. Hmm. 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 Okay, no problem. No problem. Yes, I will do. I will do. Yes, can you tell me? Efficiency is output power by input power. Output power, how much he has given? Output power only we need to calculate. So efficiency 15%. Insulation how much? 750 watt per meter square into area of module will be how much? Can you tell me? Excuse me. Sir, what happened? Am I audible? Are you there? Okay. Then can you tell me what is the power output? Efficiency into insulation into area module. 0.15. See, one numerical already we have solved similar one. Think. See, when like this it is given, efficiency we solve. How we solve efficiency? Area is 20 centimeter into 20 centimeter, 400 centimeter square. That is meters we have converted. So similarly here also you need to do this way. 1.5 to 2. How much are you getting? Are you solving? Can I show you answer? Efficiency 0.15 air. Insulation is 750 watt per meter square. Area is, it is already given in meters, 1.5 into 2. How much you should get?
Four 50 watts, sir.
No sir, can you see? I got 337.
Okay.
You have taken 1000 watt per meter square, I think.
I think so. Yes.
It should be 750 sir.
It is already given. Yes.
750 is given. Can you check?
Yes. Yes. Correct.
You might have taken full 1000.
Yes. Yes.
No. Here it is clearly mentioned that 750 watt per meter square. Fine, no? This is okay, no?
Yes, sir. Yes, sir.
Sir, no. This one can you see? A PV module has the same dimensions, 1.5 meter by 2 meters. Following parameters at test condition. Sir, here try to understand. It is following at parameters are at standard test condition. Standard test condition means, okay, so that is VOC is equal to 32.9, ISC is 30 amperes, fill factor is 76%. Okay, that is at 1000 watt per meter square and 25 degrees centigrade. What will be the conversion efficiency of the PV module at standard temperature condition and power output at insulation of 500 watt per meter square? So this is the formula. Efficiency at standard test condition is power output by power input is equal to VOC into ISC. Output is fill factor is 76% he has given. If he has not given fill factor, VOC into ISC by insulation into area we need to write. But the moment if you mention fill factor, we have to take this 76%. So 32.9 into
Into 30.
30
Into 0.76, no?
by
By 500 into
area. 1.5 into
1.5 into मतलब 3.
2 it is given. 1.5 into 2. Okay. 3. That
It's
is
2
total
na?
is 3.
3.
Yes, yes, yes. So 2.9 into 30 into 0.476 by 500 into area is 1.5 into 2.
Into 2, yes.
How much are you getting?
65%, sir?
65. Sir, 1 second. Okay. I need to change it to 500, sir. 32.9 into 30. At standard testing conditions is 1000 I need to write.
Okay.
Here I have written at standard test conditions is 1000 I need to write. And at these conditions it should be varied. Okay. At standard test condition is
And the
it
first
should be
condition is a standard condition. Okay.
so second condition should be taken at 500.
500. Second time
it,
500. Okay.
yes, yes. This one you see. A consumer is in need of 2 kilowatt solar photovoltaic energy system. He want 2 kilowatt system with output voltage of 120 volts. He want 2 kilowatt 120 volt system. For the design of PV system, he uses the PV modules whose output voltage is 10 volts. He want 2 kilowatt system and output he want is 120 volts. To get 120 volts and 2 kilowatt system, he is using output voltage PV modules are each PV module is 10 volts and current as 1.66 amperes. So now we need to design how many number of series parallel connection of PV modules are required. To get 2 kilowatt power, 120 volts, how many number of series or how many number of at least modules are required, PV modules. So what he has given, number of modules to be connected in series. How to calculate? Number of modules to be connected in series will be, how to calculate? It is total required voltage by voltage of one module. Am I clear? Number of modules to be connected in series in the string will be total required voltage by voltage of each module should be written. So we have one module of 10 volts. We want output voltage is 120 volts. So how many panels are there in the series string? In one string, how many panels are connected in series?
12 modules.
12 modules are connected in one string. But how many strings are required? Sir, how many strings are required?
I think 12 strings are required. No?
12, check sir properly.
10.
So how? So
total power is 120 strings are required, I think.
Why? See, you want 2
total
kilowatt
power
power.
Is given at 2 kilowatt.
2 kilowatt power is given.
That
so total power
divided by per cell power.
Per cell power. Per cell power, how much you are getting? Per cell power is
16.
10 into 1.66.
16.
So 16.66. So that is
divided by total. Total is divided
by that. So then total by 16.66 if you do also it will come.
12 by 10 I guess.
Yes sir, yes sir. So what will happen? 120 volts by 10 you will get number of Try to understand. 1 minute.
Yeah, parallel strings.
So number of series connections and number of parallel connections I need to decide. So number of this series side is 10 are there, and this side how many? Sorry, this side how many are there? 12 are there. This side how many should be there is
10.
10 should be there. 2 kilowatt power by voltage into one module current I put, that is 10. Is it okay?
Yes.
Our total voltage into total current also will give you.
Either of the way you can calculate.
Yes, yes. Is it fine?
Yes, yes. Very nice example, sir.
Last, a PV module with fill factor of 76% is having open circuit voltage of 32 volts. A PV module with fill factor of 76% is having an open circuit voltage of 32 volts and short circuit current of 7.8 amperes. What should be the current axis intercept, voltage axis intercept, and maximum power identifying in the IVPV characteristics if the PV panel is designed when 6 modules are connected in series? Second is 6 modules are connected in parallel, 6 series parallel array topology with 3 in series, 3 in parallel. So first one, what is given? So voltage axis intercept will be, how much it will be? VOC I want to calculate. So total 6 modules are in series. One module voltage is how much?
32.
One module voltage 32. 6 modules are in series. How much it will be?
32 into 6.
6 modules I connect in series.
192.
So 6 modules are in series means VOC into number of modules in series. So it is 192 volts. What about the current? 6 modules are in series. What about the current series configuration?
46.8.
Sir, modules are in series. If modules are in series, voltage
current
will be
remains the
added.
same. Sorry, current remains the same.
If modules are in series,
Current remains the same.
voltage will be added and current will be same as one module.
Yes, yes.
That's why I have given mistake we will do. Second one. Now 6 modules I am connecting in parallel.
Yes.
When I connect 6 modules in parallel, what about the voltage?
Voltage will be same, 32.
Voltage will be, sorry, power you have not calculated. Power is how much?
Power is multiplication of voltage and
yes. That is the wrong. Here fill factor is given, no?
Achha,
Fill
right.
factor is only 76% is there.
Right.
That is the reason. See, fill factor
Power.
when 76% only filled, power you can't extract 100%. So power will be voltage intercept VOC into and current intercept into fill factor I need to write.
Yes.
If fill factor not given, no problem.
Correct.
You understand how much you got? Voltage intercept 192 into current intercept 7.8 into fill factor is 0.76. How much you got? How much you got, sir?
1138.
1138. 1.138 kilowatt.
Yes.
Is it okay?
Yes.
So this is for series connection. Now you have a 6 modules are there. All these 6 modules you connected in parallel.
Right.
So now what will happen to voltage?
Voltage will remain same.
So all modules when connected in parallel, voltage will be same.
Yes.
VOC into in the parallel combination since voltage is same. Then what about current, sir?
Current will become 46.8.
Yeah, yes. Now your answer correct. So what about the power?
Power will be 1138. Remains same.
Yes. Either it is voltage connected. That's why series configuration I explained. No, that's why I want to give you here. Series or parallel, voltage and currents will differ, but the power will be, even though fill factor how much percent is there, it will be same. Now you consider a series parallel array. Now series is 3 modules are there. Okay. Parallel is 3 strings are there. How much amount of voltage will be there? 3 modules in series.
Okay.
3 strings in parallel.
हाँ तुम्हें
Oh.
वाह GST केला वाटतं GST कसं नसतं
FDP सर्व.
Excuse me. If three modules are in series and 3 by 3 structure it is, and three strings are in parallel, how much it will be? I'm audible, no?
You are audible, sir.
Okay, sir. Suddenly sound is off.
No, no, no. Some guest has come, so
Okay.
muted myself.
No. Can you please let me know? So three modules in series, 3 by 3 structure, series parallel, three strings in parallel.
Total power has increased, sir, actually.
Yes, sir. Voltage is how much, sir?
Voltage is 32.
Sir, you have only, so what I mean to tell you, you have only 6 modules are there. If six
Right.
modules connected in series, 192 volts, 7.8 amperes, and 1138. If 6 modules are connected in parallel, 32 volts, 46.8. Now, out of 6 modules, 3 in series, 3 in parallel. What is voltage?
Voltage is 32 plus 32, 64.
Voltage are 3 modules in series.
Sorry. 32 plus into 4 now.
Three in series.
32 T plus 32. Voltage is 96, na, sir?
Yes, sir. What about current? Current is through 3 strings. Yes, ma'am. Yes, ma'am. Yes. What about power? Yes.
Voltage, that's what. Power has increased.
So now why people are talking about same modules are given to you. If you connect series, you are getting 1138. If it is given to this one parallel, then it is giving same power but low voltage, high current. But medium voltage, medium current conditions, you are able to extract more. You understood, no? So TCT, these structures will give you best way. Last one. Last one. A few photovoltaic modules are connected in series parallel array. Each PV module has an IV characteristics of x-axis intercept is 36 volts, y-axis intercept is 8.2 amperes. Okay. Now we need to calculate short circuit current and open circuit voltage when series parallel array with 26 modules in series. Series parallel array, 26 modules in series, 8 strings in parallel. Can you tell me? It is of similar. in series parallel, 26 in series, 8 in parallel. 8 strings are in parallel. Sir, previous one increasing is because of 3 by 3, 9 modules we have taken. 9 by 9 modules here. That's why it is increased.
3 by 3, yes.
9 modules, not 6
Nine.
modules. 9 modules. That's why it is increased.
Right.
Power. 9 modules.
Because every cell contributes to the power only, no, sir?
Yes. And
Every
now this
cell
one.
is added.
Yes.
Yes. If
This one, can you
anything is
tell me?
added, it is definitely going to add the power.
Yes, sir. So now series parallel, 26 modules in series, 8 strings in parallel. So how much it will be? So total voltage,
936.
first one is
Voltage is 9.
current. You tell me current.
Current is
65.6, correct, madam. Then voltage is 936, correct. Yes. Now total cross-state topology. Try to understand TCT, total cross-state topology. There are 8 rows are there. Visualize. Total cross-state topology, 8 rows are there. Each row with 26 modules. Then how it should be calculated? You have 8 rows. Each row 26 modules. Do you understand? TCT. In the TCT, all are connected together. So there are 8 rows are there. In each row 26 modules are there. First row has 26 modules, second row 26 modules, like that 8 rows are there. How much it will be? Do you understand? 8 rows means? See, 8 rows means like this. In each row 26 are there modules. Like this there are 1, 2. Like this 8 rows are there. This is 8. This is 26.
8 by 26 matrix.
Yes. So how much it is? Let me erase this. Otherwise answer it. See, then I just.
Sir, power you are asking?
No, short circuit current and open circuit voltage, sir.
Okay. It will be same, na, sir?
That's what, sir. Now you tell me how much it will be. Current is how much?
Current 65.6?
No. That's why I'm telling you.
Current into 8.
Sir, visualize. There are how many modules are there?
524 current, sir?
Sir, we are having how many modules are there? 1 minute, I'll come back here. I'll show you. So, see, in the TCT structure, 8 rows are there. Each row comprises of 26 modules. So, current you are calculating, isn't it? Now, TCT I will show you. In the TCT architecture. Okay.
Generally, the solar cells are connected in TCT model, sir.
Sir, yes, sir. Sir, this is the structure, TCT structure.
Okay.
Now you see, like this. This is 1, 2, 3, 4, 5, 6, 7 rows are there. There is eighth one more row is there. In each row, then how many modules are there? Like this, 26 are there.
Okay.
What about the voltage calculation? Voltage will be,
Voltage will be
rows will be added together. No, how many number of rows are there?
8.
Voltage will be addition of row voltage. The
Yeah.
current will be addition of modules. So now the voltage will be how much will be there? 8 rows are there. How much you will get?
288.
Sir, try
Sorry.
to understand.
30.
Sir, there are 8 rows are there. 8 rows. 1, 2, 3, 4, 5, 6, 7. One more will come. Okay. Voltage will be VR1, row 1, V row 2, V row 3, V row 4, V row 5, V6, V7, V8 will come.
Yeah.
V8 will come.
V8.
Row voltage is nothing but V module voltage only.
Yes. That is
So
32.
8 into that value. What about current? In each row, 26 modules are connected. So current will be 26 times the module current.
Right.
So now when you are taking voltage, voltage will be equal to row voltage summation of all the row voltages. Now 8 rows are there. So how much it is? Now is it clear, sir?
Yes.
That's why TCT is given.
I think next problem.
TCT, can you tell
This
me?
one.
This one. In the TCT, 8 rows are there. Now current will be how much? Sorry, voltage will be how much?
36. 288, sir, voltage.
Okay, current, sir?
Current. $213 ampere.
How much you multiplied, sir? 26 into?
26 into 8.2.
Yes. Now let us assume one, I will add here. Let us assume a TCT, same, that many are there.
Okay.
Now if you have 10 columns are there. 10 columns, each column, okay. Each column comprises of
26.
maybe 20 modules.
Okay.
So how much it will be? There are 10 columns. Let us assume 10 columns means, that means 10 strings, I can say. Okay, we have 10 strings. Each string comprises of, I have a 10 strings are there.
Okay.
Now I have 10 strings I have taken. Can you tell me? How much I should put?
Voltage will remain same, no, sir? 288 volts.
Sir, try to understand. So here what happened? One string consists of how much, sir?
Acha, voltage has changed, okay. 20 volts. 20 into But number of rows are same, na sir?
Sir, I have given total 10 strings are there.
Okay.
Each string 20 modules. 10 strings. In a string 20 modules. That means voltage will be how much? How many modules are there in a string? 20 modules.
In one string there are 20 modules. Okay.
So voltage will be how much?
Voltage will be 720.
How much? 20 into?
36.
Yes. Then when it comes to current?
Current will be
Is multiplication of? No, current will be multiplication of how many strings we are having, madam?
10 strings we
String?
are having.
10 strings.
8.2 into 10.
Into 8.2.
82.
Do you understand the difference? It's fine, no? Is it okay?
So it is 5.6 kilowatt around, 5.9 kilowatt
Ah,
power rating.
Power will be. At least do you understand how to design the PV system with a fill factor, efficiency, mismatching loss, then series connected, parallel connected? Fine, no?
Yes, yes.
Yeah. Okay. So just let me explain you. See, just give me 5 minutes. Let me revise you once. See, today we have discussed about which one? Solar components we have discussed. What it consists of? We have a power source will be there. We have interfacing elements will be there. Load will be there. Always load is either AC or DC load. But what sources we are having? We can generate the power through solar parks. We can generate the power through rooftop PV system. These are famous. The future is going to be PV integrated EV charging stations. If it is a solar parks, it is connected to utility. So compulsory when it is connected to utility, then power flow control is required, and converters mandatory it is required, inverter also required. Okay, why? It is connected to grid, not to the load. When it is connected to utility, it should be connected to grid, not to the load. But when it is a rooftop PV system is there, it is connected to household purpose, or it can be connected to grid connected also. So there is, we are having charge controllers, a power flow controller, converter, inverter will be there. EV charging station is mainly used for uh, EV charging and can be connected to grid. So we have a power sources PV, solar PV farms, rooftop PV systems, PV integrated EV charging stations. If surplus power is there, battery can be there. So charge controller will regulate the power supply, and power flow controller will be used extended version of a charge controller, where we will introduce like DSTATCOM, DVR, UPFC. Those things can be considered in high voltage systems. Or else normal power flow controller is which will try to consider a regulation of the voltage and currents. Next, energy meter is the mainly to maintain the consumption and as well as injection values, how much it is there. Okay. Next we have seen about standalone system. When it comes to standalone system, it is not connected with the grid. How much about amount of power you have consumed, that much amount of power will, sorry, how much amount of power is generated, which will be consumed by your house itself. Okay. So here also charge controller, converters, inverters are required. Mandatory is compulsory battery is required for a standalone system. Especially in islanded situations, battery is mandatory. But when it comes to the grid connected system, I told you, so what is required? Solar farms are there. Solar farms are should be connected with the converter as well as inverter and to the grid. And rooftop PV systems and commercial buildings, no. So it is also to be connected with the converter inverter, but in a different fashion. How it is, I have shown you here. Architectures, we have a central architecture is there, string and multi-string architecture is there. Okay. Central system is mainly for rooftop PV system we will consider, because all panels together, small rating is there. For small ratings, central inverter is fine. Medium power ratings, buildings, other things, string level, one converter inverter can be connected, aggregated. When it comes to big solar plants, then we need to have multi-string conversions need to be required. Is it clear? Any queries in this? Can you tell me? So that
Sir,
then, yes, sir.
just a small query.
Mm,
Having, suppose I have my X load at my home,
mm.
so there is a system what is known as battery inverter system,
Yes, sir.
and against that we have a solar PV system, right?
Yes, sir.
So how cost benefit analysis can be done for both of these? Because I have seen that many of times people are using inverter, battery inverter system
Yes, sir. Yes,
rather
sir.
than going for
See,
solar, solar battery.
sir, what happens, sir? If you have a three-phase supplies, other things are there. If you want to generate the more amount of power, online grid, if you are connecting, then maybe sometimes PV may be useful. But now you have a small amount of load is there. But PV when you are keeping, so now government is giving you incentives. Try to understand.
Right.
See now the PM has announced like 1 crore solar power like that he has given. So each house 3 kilowatt power subsidies he is giving.
Okay.
Under subsidy if you able to buy, yes, it is reasonably cost will be lesser.
Okay.
Beyond that, if I want to install, then it will be a little bit costly. But the thing is, how much utilization is there, at what rate, and again you are connecting to the grid, that also matters, sir. Try to understand. So from the grid, when you take normal rate tariff,
Okay.
power consumption of it is 0 to 100 units is free. See,
Okay.
100 to 200 units little bit charge will be there.
Yeah,
300
yeah.
to,
Right.
it's not flat rate tariff. So it is
It's
unit
a pocket.
consumption wise. Yeah,
Yeah.
understood. No. Now what
Okay.
happened when you are giving back to the grid also, how much rate we are purchasing, how much rate we are sending, that one also we need to see, na, sir.
Yes, yes. Okay.
So if it fulfills, yes, we can take. But the thing is, for installation purpose, other things, anyway, government is giving incentives.
Correct.
Definitely, you are not utilizing so much money. You are
So,
using extraction of the this natural energy only. If your building is height permits, there is no shadow effect is there.
right.
Nearby height buildings are not there. Yes, you can go ahead.
We have to
Or
go
else,
with the hybrid model in this case also, I guess.
yes, sir. So both grid connected, we can go.
Right.
Uh,
Thank you, sir. Thank you so much.
uh, is it okay today's one? We have seen about which one? Standalone systems, grid connect PV system, hybrid. Then architectures also we have seen, numericals we have seen.
Yes.
Any queries? Yeah, understood or not? Is it okay?
Yes, sir. Okay,
Fine.
sir. Yeah.
Tomorrow we will see. Definitely this one we will see. Which one? List of solar parks I will explain. What are all the sources we are having? What are all the biggest solar parks available in India? The applications of these things I will explain. Then MATLAB session I will explain tomorrow. Okay, how to design so PV cell, PV module, this parallel TCT architectures are there. No, how to simulate in the MATLAB, I will try to explain you. Is it okay?
Yes, sir. Yes. Sir,
Please
are you going
come.
to explain the penetration effect also on the grid?
I will try to see, sir. Maximum I will try to explain you. But the thing is, MATLAB session I am keeping more time. If time permits, definitely I will explain you, sir. Okay.
Sure, sure. Thank you, sir. Thank
So, but tomorrow mainly I focused on applications and this one, sir, which one list of solar parks and MATLAB simulation. Once it is done, more time I will spend on whatever the queries are there. Then and there, the more I can explain you, whichever is there. Okay, sir.
you. Yeah, yeah. Sir, is
I
it
will
possible
try.
to take the session on in the morning? No.
Morning tomorrow, I have lectures are there, sir. To BTech and MTech
I
classes are
guess
there.
because this is at the fag end, maybe because of participants, they are less in number.
Sir, we can do one thing, sir. Maybe quickly, little bit of 1 o'clock to 4 o'clock also. I don't have any problem. Early sessions, 1 or
Yeah,
two
yeah.
o'clock.
No, no problem. In between, sir, 9 to 4, anytime people are available. But
Sir,
any,
that's what I'm telling. Tomorrow, Friday, since it is Friday,
yeah,
even if you ask me to start, even at 1 o'clock, I'm ready to take. Even 2 o'clock, I'm ready. You let me know. You consult with your coordinator, madam. She is there. You consult with that coordinators. You let me know timing, sir, with
Sir,
other
2
people.
o'clock is okay, sir. 2 o'clock.
Then tomorrow 2 to 4 we will have
No
a
problem.
session. Is it okay?
Yes.
What about others? Is it okay for you people? Okay. Then MATLAB nicely I can explain you people and
Yeah,
other
yeah.
things.
You can
Happily in
little bit
4.
extend also. No problem, sir.
Yes, sir. 4:30 as per
Yeah,
the
yeah.
timings we
That
can
is okay.
explain.
That
Okay,
is
na
okay.
sir.
Yeah, sure.
Okay.
Thank you,
Thank
sir.
you.
Thank you.
Thank you, sir. Any queries? Thank you,
Madam,
madam.
please convey the other participants also that the session has been keep on. Yeah, just by 1 hour. Okay. Thank you.
Oh, thank you.
Thank you, ma'am. Yeah.
Thank you. Thank you, madam. Bye.